Okay, I wanted to continue from last time with one last exercise before we go back a little bit to looking at actual different sorting algorithms. I wanted to do a demonstration on, hopefully from lab already yesterday, you realize why it's so nice to have this generic kind of programming thing, where you don't have to rewrite, let's see, where's the picture? You don't have to rewrite the entire sorting algorithm every single time. You did this with selection sort. You probably wrote, I forget what we had you do, but you wrote selection sort, and then you improved it by making it more generic to use a comparator. Then you could reuse that implementation over and over again. All you had to do was write a new comparator, and the sorting algorithm was fixed. All right, the sorting function was fixed. Let me go ahead and show you. What I want to do is I want to give a little bit more detail on how that would actually work internally. Like, what would the inside of Quicksort actually look like? Or what would the inside of bsearch actually look like? And to do that, I wanted to go through a really quick demonstration here of generic programming so that you can avoid duplicate work. And to do this, we're going to write a generic getMax function. So given an array of things, you want to go through it and you want to find the largest one according to some criteria. Now, if it's a bunch of integers, then you want to find the largest integer. If it's a bunch of doubles, yeah, go ahead and find the largest double. If you have a bunch of strings, you can find the largest string. If you have a bunch of students, you can find the largest student, whatever that means, probably GPA or the one with the, whose last name starts with Z, right? That would be the largest one if you use that comparator there. So let's go ahead and go over here. First of all, to demonstrate why this is so nice and why generic programming, tdlib there, is so useful, let's go ahead and write a straight up getMax function with, that's not generic, that's really specific, that it only applies to integers. We'll go ahead and make it return an integer. In fact, let's go ahead and document it. This function finds the maximum integer in the given array and returns its index. All right? So this should be pretty straightforward. You've done maybe a half a dozen exercises like this. When you did arrays, you were asked to find a needle in the haystack. Now your criteria for finding the needle is just a little bit different. You have to find the maximum, right? I'll go ahead and call this getMaxInt because I've already set up some tests down here. What do I need to pass into this function? Well, I need to pass in the array. I'm not going to be making any changes to it, so by now it should be just standard const int star arr, right? That is an integer array. It's a pointer to the integer array. It's const, so we're not going to be making changes to it. What else do you need to pass in? The size of the array, right? Now, we're not, this is not like linear search and binary search like we looked at previously. We're not trying to search for a particular needle. We're trying to search for the maximum. So there's no key that goes into this function. Here's the array. You tell me where does the max exist. So we'll start out by making an assumption. We'll go ahead and create an int max index, or index of max if you want to call it that. I'll start it at the first one, 0, right? Now I'll go into a for loop here, and I don't need to start at 0 because I've already assumed, well, we'll go ahead and look at the first one, and then we'll compare it to everything else until we find something that is larger than what we found so far. Then we'll update our index to point to that thing, or to refer to that thing. Then if we find something else that's larger, we'll update our max index to that. So I'll start at 1 because I've already started at 0. I don't need to compare the 0th element with itself and then find, oh, do I need to update the index? Well, it doesn't change no matter what. So int I is equal to 0, I is less than n, I plus plus, pretty standard. And an if condition here. If the ith element, that is array sub I, is greater than the element stored at max index, then we've found something larger, right? So we need to update our max index to be I. Right? At the end of this loop, we found the element, the maximum element. It's stored at index max index. So we'll go ahead and return max index. Okay? So that's a pretty straightforward, easy implementation of getMax. But of course, as the name implies and as the signature implies, it's only good for integers. Right? This is a one-shot solution. Let's go ahead and make sure it works, first of all. I didn't put any testing code. Okay, so let's go ahead and finish this out. Printf max found at index %d, %d with value %d and the line. So I'm going to go ahead and print the index and the array of index. You'll note here that I don't have a sorted array. Otherwise, if I had a sorted array, if I knew that I had a sorted array, where would the maximum be? Right here at the end, right? So I would just jump there and say, okay, there it is. I'm not going to make that assumption, though. I'm not going to make the assumption that it's sorted, so I need to find the max. Now, the maximum is 9, and it should be at index 4. Right? Yep, found at index 4 with a value of 9. So we're okay that this is pretty straightforward code, and it works. But again, it's a one-use code. It's only good for integer arrays. If I wanted to make this good for double arrays, well, I'd call it something different, double, and then I'd change its signature, but of course nothing else would change. If I wanted to make this for strings, find the maximum lexicographic maximum string, I would again cut, paste, and redesign. My greater than sign here would change into a call to strcmp, though. So what I want to do is I want to take this and make it generic. I don't want to have to write a version for every single type that's out there, or every type that I might create in the future. The maximum student, by what criteria? There could be dozens of different criteria. The maximum bank account, right? What do you mean the maximum balance, the maximum APR, the maximum ID, right? I don't want to have to worry about those things. I want one solution that will work for all of those. And then you give me a comparator, and I'll use that comparator. So I'm not going to call it max int anymore. This function finds the maximum element, right? We're no longer saying it's an integer. It's just a generic element in the given array and returns its index. Okay? So it's no longer going to be an integer. I cut and pasted this, and we're going to now modify it. We're going to take away anything that is specific to an integer. So const void star array. Now it can point to anything. Now it can point to an integer array, it can point to a double array, it can point to a string array, right? Or an array of strings. Okay? There's something else that we need here. That's going to be int size. And we'll understand what that means here in a second. But you saw that when you used Quicksort and bsearch, etc. You passed in the size of each element, because in Quicksort, if it needs to swap these two things, it needs to know how many bytes is this and how many bytes is this, so that I can copy this bytes over here and I can copy these many bytes over here and exchange it. Right? We're going to need to know how many bytes each element takes. Also, we're going to need a comparator. Right? So int star. In fact, I don't even want to bother with this. Man, Quicksort. I'll go ahead and cut and paste this. There's my comparator signature. Right? Otherwise, that's a lot of typing. And I could get it wrong. So there we go. It takes a comparator now. So it takes the array, it takes the number of elements in the array, it takes the size of each element, and it also takes a comparator now. Right? Why do we need this comparator? Well, we'll go ahead and maintain the maximum index, and we'll go ahead and iterate over each element in the array like normal. But this is no longer operable. We can't simply use a numerical comparison operator here because the elements stored in ARR are not necessarily numbers. Right? They're not necessarily integers like they were before. They could be strings, in which case this doesn't make any sense. I would have to use strcmp. They could be students, in which case I would need to have more complex logic. But that's where the comparator comes in. Okay? Let me go ahead and use this comparator and pass in these two values. Right? Now, now we're still not done here. The comparator requires what? The comparator takes two const void star elements. Is ARR sub I, is that a const void star element? ARR is a const void star element, but then when we index it, the ith element, it's no longer a pointer. Right? Now what is it? Well, now it's just a const void something, right? So we can't do this, right? We have to rethink the elements here, right? Let me go ahead and take care of that before the if statement here. What we want a pointer to the ith element, and we want a pointer to the max index th element. Right? How do we get a pointer to those elements? This is where the generic programming comes in. Now we have to think at a lower level. Now we have to think in terms of memory addresses. Okay. For that, let me go ahead and go to the overhead projector here, if I can. .cam. There we go. Does that work? Good. All right. So remember, we have this array, right, of elements. And how many? Here's the 0th element. Here's the first element, or by index here. 2. ... Right? Now we have a pointer to the first one. That's ARR. That's pointing to this memory address right here. Okay. How many bytes does each element take? We gave that to the function for a reason, and now we're going to use it. There are size bytes here. Okay. There are size bytes here. There are size bytes here. So let's just take the second element here. What address is that located at? Well, the start of the array is at ARR, right? How many more bytes are over here for the second element, or for the third element at index 2? How many bytes? How many bytes? It's going to be 2 times size, right? What about this third element here? Let me go ahead and ... And then we'll generalize this to the ith element here. What about the third element? How many bytes over is it? Size, 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 and there's the third element. So it would be at ARR, 3 times size. And what do I do with these? I add them, because this is an offset. This is how memory works. This is how arrays work. I don't need to know that this is a 4-byte integer. I don't need to know that this is an 8-byte double, or an 8-byte pointer, or whatever, or a 40-byte student sitting in here. All I need to know is how many bytes do I need to jump from this address to get this element right here. So at the ith element, ... what would be the general formula? I times size. Right? This is where you use your index. This is where the memory address begins, and so these two things together give you an offset for it. Right? That's visually what it looks like. What does it look like in code? It's just simple. Well, it's exactly that. Let's see. Go back to this. I want a pointer to the ith element. I want a const void star pointer, right? And I'll call it A. And it's going to be at the ith element is going to be array plus I times size. Right? Now again, array, that is a memory address. When you have a const void memory address and then you add a couple of integers to it, right? Then you are doing pointer arithmetic. I'm no longer adding numbers like 5 plus 10 is equal to 15. I am treating memory addresses, and then I'm adding an offset to that. I'm jumping to a different memory location. You can, of course, do multiplication. You can do division to go backwards, right? You do this all the time. In fact, you did this up here. Anytime that you did sub I with the square brackets, this is what the compiler was doing. It was just doing the math for you. Well, we don't have the luxury of the compiler doing the math for us now because the compiler doesn't know what this is. It's a generic void pointer. Only when you tell it the size can you do, when you tell your function the size, can you do the pointer arithmetic for yourself. Now, what does the other one look like? Const void star b equals array. That's where you start again. But now you use the max index times size. And then you can plug these two things into your comparator. Now I'm comparing A, the current element, to B, the thing that I've found so far that is the maximum. When do I want to update my max index here? When the current element that I'm looking at right now, A, is larger than the maximum element that I found so far. What would the comparator return if that were the case? Just plug in some numbers if it seems confusing for you. A is larger than B, okay, 10 and 5. 10, 5. What should it return? Something positive. So if the comparator returns something positive, then we need to update our max index. Okay? And then at the end, we'll return our max index. The only, you can do this pointer arithmetic a lot more efficiently, a lot more compactly, and take out the comments. I'm doing this for demonstration purposes. Okay? Now let's come down here and actually use it. So instead of using getMaxInt, I'm going to use getMax. I will still pass in the array and the size, and now of course I need to pass in the size and the number of bytes of each element, so that's going to be int. And then I need a comparator here, which, oh, I never wrote my comparator. So let's go all the way up here and write a really quick comparator like we did last time. As a review, int, cmp int, right? And what does it take? Does it take two integers, a and b? Is that a comparator? Nope. Does it take two const int star pointers? Is that right? Nope. It has to be generic. It has to be void pointers. Okay? Then you can typecast them. So const int star x is equal to const int star of a. You're typecasting them. And then y is going to be a cast of b. We're going to avoid the difference trick like we did last time. If dereference x is less than dereference y, then we'll return -1. Else if dereference of x is greater than dereference of y, return 1. Else they're the same, so return 0. Right? Now I will pass in my comparator. Let's see, hopefully I didn't make a mistake here. We should get the exact same result as before. Max found at index 4 with a value of 9. Hey, we did it. What if I put in another max? What if instead of 2 we had 42? We should expect it to return an index of 1, the second element there, with a value of 42. Right? Great. Now, what if instead we had doubles? Right? 40.5, 3.14, 62.89, right? 87.3, right? 87.3 will be the largest that I just put in there. Do I need to rewrite my getMax function? Nope. What do I do instead? All I do is change the types, right? Now they're doubles. I didn't add anything, did I? Nope, there's still 8 elements. And of course I will need to change my comparator. I don't have that here. I had that from last time. Let's go ahead, cut, paste, and this will be for a double instead. Double, double, double. But otherwise the logic is exactly the same. Right? Let's come down here. Let's run it. We should get 0, 1, 2, 3, 4, 5, and a value of 87.3. Again, I'm going to go ahead and cross. Oh, and then print statement should be printf, and the index would stay the same. There we go. All right, so, darn it. What was wrong? Oh, where? Oh, thank you. Which one? There we go. Double. I didn't change the function name. Right? That's the risk of copy pasta there. All right, max found at 5 with a value of 87.3. And if we change this to 104.2, it'll find that new max at index 4 with a value of 104.2. Right? What have I done here? I have written a getMax function, just like somebody wrote that Quicksort algorithm and put it into the standard library. They've solved the sorting problem forever. Right? They have one generic solution that you can reuse infinitely. All you need to do is create a brand new comparator instead of rewriting the algorithm every single time. And what have I done today? I've solved the getMax problem forever by having one solution that will work for any type. All you need to do is provide me with a comparator to say that this thing is larger than this thing, so it might be the max. It's definitely not this thing over here that's smaller. Right? All you need to do is keep things generic. And by the way, I've also solved another problem. What about a getMin? you could copy paste this and change this one character here to be strictly less than, or you could do what? Switch the comparator around, right? Last time we wrote get int or CMP int, we also wrote CMP descending. All you would need to use is that other descending, and now the maximum is the minimum with respect to that comparator, right? Cool tricks all over the place. And I've solved this problem now forever. I don't need to ever worry about rewriting the same algorithm over and over again. I'll go ahead and cut and paste this and put this into the notes so you have a copy when it gets posted. There we go. All right. So I want to look at sorting that is revisited. Right? We're going to look at some sorting algorithms today. Let me see. I need to get on the correct page here. There we go. All right. There are lots of different sorting algorithms, and you might go to YouTube or you might go to just do a Google search on sorting algorithm visualization. These things are a dime a dozen. There are lots of videos on visualizing sorting. There are some funny videos. I think somebody posted one to Piazza about a bunch of Hungarian dancers demonstrating Quicksort. It's a very popular topic because there are a couple of dozen different sorting algorithms that each illustrate a different algorithmic strategy. I'm going to focus on two of them in this course because I don't want to focus on algorithmic strategies. I want to focus on efficiency. I want to show you a really terrible sorting algorithm and show you why it's terrible. Then I'm going to show you a better sorting algorithm and show you why it's awesome. Right? So let me go ahead and start out with the bad one first. Selection sort. So here's the basic idea. Search through the array and find the minimal element. This is basically what we just did, but instead of finding the maximum, we found the instead of finding the minimum, we found the maximum, right? Once you've found this, swap it with the first element. So if I go through and find the minimum element, oh, here it is, and I swap it with the one at the beginning, where is the minimum element now? It's at the beginning. So you would say that the first one is where it needs to be. That's where it belongs. Now all I have to do is repeat that process for the remaining n-1 elements. Go through the rest of them, find the minimum among those, and then swap it with the second element. Then go through the remaining n-2 of them, find the third smallest element, and put it at index 2. Right? So you repeat. Find the second smallest among the remaining n-1 elements, and swap it with. I'll call this ace of or ace of 1. Right there. I'll backtick it instead here. Sorry, bear with me on formatting. There we go. We'll swap it with ace of 1. The first element being, of course, ace of 0. Right. Then, in general, on the ith, I'll go with this ith iteration. The first i-1 elements have been sorted. So search the remaining n-i elements and find the minimum. Swap it with, and I'll go ahead and backtick this one to ace of I. Right? So that gives us a general approach here to develop a selection sort algorithm. I'm going to go to the overhead projector here because I want to show you something else. Let's go with this. Let's develop this algorithm. This is a basic idea. This might be how a human does sorting. Okay. What I want to do is I want to take a cue from what we just did with generic programming. I want to solve this program, or I want to solve the problem of sorting, not just for an array of integers in C, and not only just for anything in C. I want to solve it at an even higher level. I want to solve it conceptually. I want to develop an algorithm. And for that, I'm going to, instead of writing C code, I am going to write pseudocode. Pseudocode being fake code. Pseudo, fake, code, right? So what I'm going to do is I'm going to start just giving a general process here. This is not going to be C code. This is not going to be Java code. This is not going to be Python code, right? Instead, it's going to be pseudocode. There are no hard and fast rules about pseudocode, by the way. If there were hard and fast rules about what you should write when you write pseudocode, guess what? You've got a programming language, right? And that's not what we want. So my input here is going to be a collection of elements. I'll even give it a name, A, of elements A1 through AN. Okay? And, yeah, that's it. Did I say that this was an array of integers? Nope. I made this even more generic conceptually. This is definitely not syntax that, well, it's kind of like syntax that's allowed in C, but you definitely can't go ... and the indexing is different. In fact, the first element is at index 1. That's not programming, that's math, right? I'm keeping things general. I'm going to use plain English. I am going to use mathematical notation in favor instead of actual code, right? Because I want to keep this at a high level. Our output will be A sorted, right? This is not a function with parameters. This is not a program with a main entry point. This is just a pseudocode, right? All right, help me out here. How would I go about with that idea? I wish this were a whiteboard instead, and then I could go ahead and erase things, but as it is, I'm going to have to do it right the first time here. There's obviously going to be two loops here, okay? I will come back and fill in the blanks for I running from something up to something. What I'm going to want to do, and you can use comments, by the way, in pseudocode. That's perfectly fine. I'll go ahead and put the comments in here. Let's see. Find the minimum element. Should I switch to blue? Let's see. That little bit, yeah, that's a little bit darker. Let me go ahead and switch to blue. Find the minimum element among. Now remember, this is the ith iteration, so the first I minus 1 elements have been sorted already. Okay? So what we want to do is we want to find the minimum element among a sub I, ... up to the end, a sub n, and then swap it with a sub I. So help me to write a loop here. Right? What I'm going to do is I'm going to take care of I'm going to keep track of the index first, right? So let's call it min index. This is something new. I will go ahead and keep track. I'll initialize to I. Did I use equals here? No. I used a left arrow. Not every programming language uses an equal sign as the assignment operator. Maple, for example, uses and I think older versions of COBOL, I'm not sure, but uses a colon and then an equal sign. Don't quote me on this, but I think Haskell, or maybe, no, R. Does anybody have any programming experience with R? Or heard of a programming language called R? It's like a statistical programming language. They use a less than sign along with a hyphen. Well, what does that look like? It looks like a left arrow. This simply means take this thing and put it into this thing over here. In fact, there are a lot of people who think that using the equal sign for the assignment operator was a mistake way back when C was developed, because you're conflating it with the algebraic equals. That's why you have to have equals equals. And that's why in non-statically typed languages like Python or PHP, you not only have equals, which is going to be an assignment operator, equals equals, which is going to be an equality tester, a loose equality tester, but then you have three equals, equals equals equals, for a strict equality testing operator, right? But I'm not going to do any of that stuff because I don't want to have to worry about that. Right? I want pseudocode. I want a high-level description. I could have even written this in English. Place into the variable min index the value I. Right? Then I'll have another for loop here. For j running from I plus 1 all the way up to n. Right? Again, that's not C code. What I'll do is I will compare if a sub min index is greater than a sub j, then that means that we found a smaller element, right? A sub j is a smaller element than the smallest element that we found so far. So I will update my min index. Basically, we just did this, except that the greater than sign would have been inverted. Min index will be updated to j. Right? Ooh, look at that. Did I write this code, this pseudocode with opening brackets, closing curly brackets? Nope. That's because there are languages, Python for example, that don't use opening and closing curly brackets to denote blocks. Instead, they rely on indentation, which is kind of a mistake, but so be it, right? Instead, I'm using something completely different. I'm using these vertical lines here, and again, there are no rules. You don't have to do it this way. You could have used curly brackets if you really wanted to, but what I'm doing it like this because there is no way for you to mistake this as pseudocode. There's no coding language that allows you to do this. To get this kind of style, you'd have to, like I use in the book, you would have to use LaTeX, and then would typeset it like this. Okay. Once I've found the minimum, I'm going to swap it. Swap a sub I and a sub min index. Right. Pseudocode, the beauty of it. I'm using plain old English. Normally, you would have to say, put a sub I, or sorry, a sub j. No, a sub I is correct. Put a sub I into a temporary variable, take a sub min index and put it back over there, and then take the value stored in your temporary thing and put it over there. In other words, 3 lines of code. I don't want to have to deal with that. Right? I know that anybody who can write code can translate this into whatever language they've got. In fact, in Python, this would actually be a one-liner, right? Because you can swap things on one line. All right? There, that's it. Now I just have to determine what my eyes should run for. If I just look at I'm going to probably want to start where? I'm going to want to look from a sub I through a sub n for the minimum. So I'll start at 1. But where do I need to end up? If I've sorted the first a sub n minus 1 of them, do I have to sort the last one? No, it's already where it needs to be. So I only need to go up to n minus 1. Now, again, this is one indexed. If you, the whole point of writing pseudocode like this is that you should be able to, that if you know a high-level programming language, or any programming language, you should be able to take this idea and translate it to C. You should be able to take this idea and translate it to Java. You should be able to take this idea and translate it to whatever programming language you're using. Right? That's why we like to use pseudocode. It's a more general, algorithmic kind of description of a process. Okay? I won't translate this to C because we gave this to you as part of one of your assignments so that you could use it. Right? What I want to show you, though, is how terrible it is. Okay? Let me go ahead and put this up. Unfortunately, we're going to get into some math here, so it's just algebra, though. We'll get into calculator. Don't worry. Is that too see-through? That's fine. Okay. So my question is, how many comparisons? Or, you know what? How much work does selection sort do? All right. So let me go ahead and go back to the pseudocode here. And what kind of work is it doing? Well, it's doing a loop. So it's got a variable, and it's incrementing that variable by 1. And it's doing a comparison to see should we break out of this loop. It's doing an assignment. It's doing another loop with another loop-controlled variable, right? It's doing another comparison. It's doing another assignment. It's doing a swap. There are lots of candidates here for narrowing in on what work means. If I were to actually run this on a computer, though, what kind of work does a computer do? What kind of resources does a computer expend? Say what? Clock cycles. In other words, time. Right? It takes time to compute something. What's another resource that a computer uses? Memory. Right? How much extra memory does it take to sort something? Right? Or another way of looking at that is going to be a memory read and a memory write, right? Because a swap, now these are all engineering questions. Maybe it's more costly on this particular system to do a swap than it is to do a comparison or something like that. In which case you would want to focus on this down here. What I'm going to do though is just going to say fiat and say I want to focus on this operation right here. How many comparisons does it make? Now, granted, there are comparisons up here to see if it should jump out of the loop. There are comparisons here to see if it should jump out of that loop. There are assignments. Those are costing you CPU cycles. I want to keep it simple, though, because all of those other things will fall under the category of a bunch of constants sitting out front of my final answer. I'm going to focus on this one operation, okay? How many times, and now what I'm going to do is I'm going to go ahead and label these lines, 1, 2, 3, 4, 5, 6, and 7. Right? So my question here is how much work does selection sort do? I'm going to change that into how many comparisons does selection sort make? And I'm going to keep it general. So to sort a collection of n elements. That's my question. Right? Now this is where the math is going to come in. So how many times, what I want to do is I want to focus on we call this an elementary operation. I want to focus on that comparison there. And then I want to go ahead and zoom out and find out how many, count up the number of times that comparison is actually executed. But if I just focus on, I don't even know what that is. If I just focus on line 5, how many comparisons does it make on this line, this one line? If I look at that in isolation, just one. Right? So now what I need to do is I need to look at this as a block and ask, how many times is this block executed with respect to its enclosing loop? Okay. So I'm going to start a summation. This is line 5, right? Yep, line 5. It's executed once on each iteration of this for loop. So establish a summation. J is equal to I plus 1 up to n. That's the loop. Now I zoom out further. This is lines 4 through 6. All right, this is lines 4 through 6. Okay. Now, how many times is this block executed right here? This block from line 4 to line 6 executed. Well, it's in this for loop up here. So establish another summation. It runs for I running from 1 up to n minus 1. 1 up to n minus 1. Right? And there you go. All you need to do is solve that summation now. Right? It's not that hard. Let's go ahead and do it. I'll do it on the overhead projector here. If I don't run out of paper. Yep, there we go. All right. So there's my summation. I'll put it up towards the top here. Let me go ahead and rewrite it, and then we'll derive it. 1 summation of j running from I plus 1 up to n. And the summation on the outer one is I equals 1 up to n minus 1. Okay? There's my summation. What is it equal to? Well, to solve summations, you work inside out. And so I just need to solve this summation first of all. It's going to be 1 plus 1 plus 1 plus 1. How many times? It runs from j as I plus 1 all the way up to n. So how many times does that run? So think about I plus 1, I plus 2, I plus 3, ... all the way up to n. And there's only 1 on each one of these. 1 plus 1 plus 1 plus 1 plus 1. What is this summation right here? Well, how many came before it? If you had started out at 1 instead. 1, 2, 3, ... all the way up to I. And these are 1, 1, 1, plus, 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 ... How many are here? If I count up to I and I go 1 plus 1 plus 1 plus 1, what if I is 5? 1 plus 1 plus 1 plus 1 plus 1. What do I have? 5. There are I of them here. How many of them are total? N. So how many of them are right here? N minus I. Right? So this, don't lose your outer summation here. 1 up to n minus 1 of n minus I. Okay? So we've simplified it. Now, the summation of sums, this is a sum, this is n plus negative I. So I can split this up into two summations. Let me go ahead and go down here. Is equal to summation of I, 1 up to n minus 1, of n, minus summation of I running from 1 up to n minus 1. Okay? I just split this into two summations right here. Okay? What's the first summation? This is n plus n plus n plus n. How many times? 1 up to n minus 1, so it's going to be n times n minus 1. Minus. Now what is this thing right here? This is different. This is 1 plus 2 plus 3 plus 4 plus 5 all the way up to n minus 1. You might not immediately recognize it. You might not have ever seen it. But here's the story. There's a kid called Gauss, and he was kind of annoying his teacher and his tutor. And so this is the apocryphal story. I don't know if it's true or not. And his tutor said, "All right, quit bothering me. Go do some summations. Add up the numbers 1 through 100 and tell me what it is." So he goes off for 2 seconds and says, "Oh, it's 5,050." How did he come up with that answer? This kid came up with Gauss's formula. The sum of natural numbers, 1 plus 2 plus 3 plus plus n, is equal to n times n plus 1 all over 2. Right? It's a pretty standard induction when you're introduced into induction. It's Gauss's formula. Right? Where have you heard Gauss before? Gaussian distribution, a normal distribution, Gaussian elimination, Gauss-Jordan elimination, et cetera, et cetera, et cetera. Right? So we can use Gauss's formula on this. Instead of n, it's going up to n minus 1. So this would end up being n minus 1 times n minus 1 plus 1. So that cancels out. And it's going to be n times n minus 1 all over 2. That's really convenient because the second one is half the first. So when I subtract it and take its difference, this is simply just n times n minus 1 all over 2. What's the most, you can expand this out if you really want to, 1/2 n squared minus 1/2 n. What's the most important term there? N squared. Why is it, what do I mean by important? What was the whole point of this? We were trying to capture the amount of work that algorithm performs. The amount of work grows, right? If you grow the input size, if you grow the array that you're trying to sort, then it's going to take longer to sort it. This captures that growth. What would you say, now if I ignored the lower order term here, if I ignored the constant, which is not going to matter for a computer anyway, then you would say that this is, that if I wanted to use selection sort to sort an array of size n, it's going to take me about n squared operations, right? How bad is that? What characterize this? Is this a linear function? Nope, it's a quadratic function, right? So the takeaway from this is that a selection sort is a quadratic sorting algorithm. Okay. Let's go back to the notes here. All right. So analysis, again, cut and paste from the handwritten part here. But the analysis is how many comparisons does selection sort make on an array of size n? it requires about n squared operations, meaning it's a quadratic sorting algorithm, okay? In practice, those are terrible, and we'll see why here in a moment, or maybe on Monday, depending on how much we do on Quicksort here, right? So, but for any even moderately large data sets, quadratic algorithms are not at all feasible. Because think of the rate of growth of that. Now here's where I'll bring in just very, very briefly calculus. Let's go back to the written here, .cam. Again, I don't want to bring it in too much, but what does n squared look like? What does the function n squared look like? It's this growing function, right? How can you now you can call it you can call it quadratic or whatever, but what's another way of characterizing the rate of growth of this? Because n is going off to infinity here, right? This is capturing the size of your input, the size of the array that you're trying to sort, right? This is the size of the array or collection. This is time or resources. So how could you characterize the rate of growth of this function? Calc people, how do you get the rate of growth of a function? You take the first derivative. What's the first derivative of this? 2n. The rate of growth is linear, okay? So, okay, well, if we're stuck with that, so be it. I want to look at a much better alternative, though. Okay, now I have run out of paper. So, hopefully I don't run out of paper here. Okay. I want to look at another way of doing this. We're not going to develop pseudocode for this, and we're certainly not going to implement this because it's already implemented for you. But what I want to do is I want to show you how Quicksort actually works. So say that we've got 5, 7, 9, 8, 42, 1, 2, 3, 4, 5, 3, 8, 6, 7, 9. There we go. We've even got duplicates here. So the way that this works, the way that Quicksort works, is it chooses a pivot element. Now there are lots of ways that you can choose a pivot element. The ideal way would be to use the median element in your array as your pivot element. How do you find the median element in an array? Oh, that would assume that it is sorted, right? Putting the cart before the horse, then, right? We're trying to sort, right? If I could find the median, then I'd be done, right? With that trick. So instead, what I'm going to do is I'm going to take the strategy of just take the first element and treat that as your pivot element. Okay. Now, what do I mean by pivot? In basketball, if you come down, take one step, this is my foot is my pivot foot. What can you do with your pivot foot? Well, can you pick it up? Not without passing the ball, or it's traveling. So what do you do with your pivot foot? You can pivot around it. You can move around it. This pivot element, we're going to take the rest of this stuff and we're going to move it around the pivot. If it is less than the pivot, then we'll put it over here on the left. If it's greater than the pivot, then we'll put it over here on the right. And now I'm regretting my pivot choice, so let me go ahead and add in 2. There we go. All right. So let's go through these, and 7 is greater, so I'll put it over here. 2 is less, so I'll put it over here. 9 is greater than 5, so I'll put it over here. 8 is greater than 5. 42 is greater than 5. 3 is less than 5. 8 is greater than 5. And then finally 9 is greater than 5. Now what I'm going to do with my pivot element is I'm going to put it right here. What can you tell me about that pivot element? If this were sorted, it would be right there. In other words, it's found its home. It doesn't need to move anymore. Right? What you do now is you sort the left partition. We call these partitions. This is the left partition, and this is the right partition. And you sort it. Right? Well, guess what? What about the left side? That's not that interesting. Why? It's already sorted. Right? So let's go ahead and go with the right partition here and repeat that process. Here's my pivot element. Right? What I'm going to do is I'm going to go through the rest of them and put it to the left or the right. So here's 8. 42 is larger, it goes over here. 8 is less. 9 is equal. You could put it on the left or right as long as you're consistent about it. I'll put it on the right. And 7 is less, and so it would go here. Well, what about 9? It goes right here. Right? By pivoting around these things, wow, look at this. 9, 42, that's already sorted. All I have to do is sort on that sub-array right there, right, and continue it. 8 will be my new pivot element. 8 goes over here, 7 goes over here, and 8 is where it needs to be. Right? That seems a lot quicker than going over this over and over and over and over again. Right? And in fact, it is quicker in practice and in theory. Right? That's the idea. How much better is it? Let me go ahead and go back to this. Right? And again, let me go ahead and I did it all over there. Let me go ahead and cut and paste this for your notes, though, for Quicksort. So again, the basic idea is that you choose a pivot element in the array. You partition all of the elements around that pivot, putting them to the left or right, depending on whether or not they're greater or less than the pivot. You repeat by, this seems like recursion to me. Right? You repeat by recursing on the left partition and the right partition until your partition is of size 0 or 1. If I gave you an array of size 1, what could you tell me about whether or not it's sorted? There's only one element, right? Is it sorted? Yes, by definition, right? So let's do some analysis. We won't do a heavy analysis on this either. Instead, I'm just going to tell you analysis. The worst case, or worst, Quicksort can be bad. It can devolve into n squared, but the Quicksort has an average running time, or average makes. Let me rephrase this. Quicksort makes an average number of comparisons proportional to. And I don't want to write this, so let me go ahead and cut and paste it. And let me put it on its own line. There we go. N log n. Right? Is that better or worse or the same to n squared? Remember, we're capturing resources. We're capturing time. Less time is better, right? Because your computer is done faster. So if it makes n log n comparisons instead of n squared comparisons, it's way better. Right? I won't ask you to do the calc, but does anybody know the first derivative of that? You'd use the product rule, and you'd come out with one term would vanish, and the other term would end up being log n. Right? So instead of having a linear rate of growth, you only have a logarithmic rate of growth. Which one is better? Certainly the logarithmic. Logarithmic is exponentially better than linear. Right? So again, don't worry about the calculus. It only makes about n log n comparisons. What I want to do is I want to look at this not from a calculus perspective, but from a practical perspective. We're going to look at it in 3 different ways from a practical perspective. Selection sort is n squared versus Quicksort being n log n. I mean, again, I'm just telling you what it is, n log n. I'm not going to go into the details of deriving that. That would require the master theorem and solving recurrences and stuff like that. I don't want to do that. Right? From the mathematical perspective, certainly n log n is better because it's smaller. It's a smaller growing function. We call these things quasi-linear, or we call that thing quasi-linear. Right? If it's linear, then it would be n. What does quasi mean? Not quasar, but quasi would be sort of. Yeah, exactly. Half or almost. Right? It's almost linear. If it weren't for that logarithmic factor, it would be linear. How do logs grow? Extremely slowly. In fact, again, calc, unfortunately, if you take the first derivative of a log, what do you get? Just take the natural log. What's 1 over n, right? In other words, its growth rate is diminishing. Right? Instead of the growth rate is now no longer even growing. The growth rate is actually going down, right? as you go off to infinity. The way that I want you to consider this is consider doubling the input size. n. And what I mean by that is selection sort would have how many more operations? Would have the number of comparisons go from, let me go ahead and go to math mode here again. It would go from n squared to, well, if I double the input size, n gets doubled, so it's going to be 2n squared, which is equal to what? What happens when I take the square and distribute it on that 2 and that n? It's going to be 4n squared. Right? In other words, doubling the input size quadruples the number of operations that selection sort performs. Right? And by operations, I mean comparisons. Right? That's terrible. What if I went up by a factor of 10? What if I went from, instead of n, I went up to, instead of, say, 10,000 elements, I went up to 100,000 elements? How much slower would it be now? 10 times bigger would be, 10 squared is going to be 100 times slower. Right? That's because of that square factor right there. Right? Now consider Quicksort would have the number of comparisons go from, now here it's going to be n log n to what? There we go. I'll double the input size. I'll double n. And that will be 2n on the outside and 2n on the inside. Help me out here. Now I'm going to ask you about log identities. What can I do with that log identity? Log of 2n is equal to log of a times b is equal to log of a plus log b. You can split it up, okay? And when you split it up, two things happen, right? Log of 2 plus 2n log of n. There we go. That looks good. What happens to that first term? The logarithmic term here goes away. By the way, all of the logs are base 2. Why? Because it's binary, right? Log base 10, right? That would be how humans count, 0 through 9. But mathematicians decided for some reason to make e the natural base. If you take the natural log, that is ln of e, ln of whatever, then the base down there is going to be 2.17 whatever e. Why is that natural? Why is 10 not natural? Derivative. What happens to the derivative of e to the x? It's equal to e to the x, right? That's why mathematicians like it to be natural, because there's no little constant sitting out front when you take the first derivative. And that's what happens at 2.71, right? But for a computer, what's natural? Binary. So these are all log base 2, and this one goes away. And we're left with the first term, which is 2n log n plus 2n, right? So forget about that lower order term there. Focus on the largest order term here, 2n log n. Well, we went from n log n up to just 2n log n, so it only about doubles it, right? Doubling the input size only doubles the number of operations, right? Roughly, right? This is where the quasi comes in. It's not exactly double. It's a little bit more than double, but that's because of the quasi-linearity there. So in other words, it's almost linear, okay? Here's another perspective, practical perspectives. Right? Consider sorting a large array of 1 trillion elements. Okay? How big is 1 trillion? It's going to be 10 to the what? 10 to the No? So million is going to be 10 to the 6th, billion is 10 to the 9th, trillion is 10 to the 12th. Okay? If I did, say, selection sort, I would have to do roughly how many comparisons? 10, let me go ahead and copy this so I don't have to deal with it. 10 to the 12th squared, which is going to be what? 10 to the 24th. Do I have, oh yeah, I do have that name. This is 1 septillion operations. Right? There is a name for that. 10 to the 24th. 1 septillion operations. You know what? Let's go ahead and measure. Does anybody want to humble brag about their graphics card? Usually, computers are measured. Their speed is measured in terms of flops, which are floating point operations per second. Now, it's not exactly comparable with a regular processor versus a graphics card processor. But has anybody clocked their computer and want to advertise how many flops they were able to get it up to? Anybody? Oh, how did you do that? Okay. You overclocked it, I assume. So 10 to the 24th operations, right, roughly. And you did, what was it again, 7 teraflops? All right, 7 trillion, billion, million, tens, operations per second, okay? So you've got a pretty good machine there, seconds. How long is it going to take your machine to sort that 1 trillion elements using selection sort? All right. So average Gregorian years, 4.5 times 10 to the 6th. Your computer is going to be sitting there for 4.5 million years, right, sorting that array, okay? So you said 7 teraflops, T-flops. It would be about 4 million years, right? What about Quicksort? Quicksort would only make, and again, let me go ahead and copy this so I don't screw it up, log of that many. Right? 10 to the 12 log 10 to the 12. What happens to that 12, by the way, in the log? Let me go ahead and put parentheses around it to emphasize the fact that it is like that. What happens to that 12? It just comes out. 12, c dot, 10 to the 12, log base 2 of 10. Well, pull out your calculators and you find that log base 2 of 10 is about 3 point whatever. I don't care. Let's go ahead and come over here and recompute that in Wolfram Alpha. 10 to the 12th times 12 times log base 2 of 10. Right. And there we go, and put it over there. There. How many seconds is that now, roughly? All right, so still a lot there, but you're sorting a trillion elements, right? Did I get my math right? I think I did. Oh, okay. How many seconds is that? Seconds to days? Will that tell us? That's way too many, right? That's minutes? There. That's only going to take, it's only going to take an hour and a half instead. Right? Now that's still maybe not tolerable. And again, these are just back of the envelope kind of calculations. But it puts your system in a whole better light, doesn't it? Instead of 4.5 million years, you're only going to be waiting an hour and a half for that to actually compute. Right? So much, much better. Right? So let me go ahead and write that down, that it's only about 4 hours or 1.5 hours with a 7 teraflop computer. Right? And I'm sure that it would actually be a lot faster. Right? Yeah. We're not going to get into big O notation formally here, but that's basically what we're doing here is big O without getting into the mathematics of it. O stands for is actually omicron. It was, if you know big O notation, then it was invented hundreds of years ago in calc to get rid of lower order terms. But there's big O, there's big theta, there's big omega. O is actually omicron. It's just that omicron, the Greek letter omicron, and our letter O are indistinguishable. In fact, LaTeX doesn't even distinguish between them. They're the exact same character. There is no Greek letter omicron. It's O. And so that's where that comes from. That's why we call it O. It's omicron. It's a Greek letter. All right. We'll go ahead and continue this on Monday with an actual demonstration.